recording. Here we go. So the video is starting on time. Oh, and my little webcam thing is frozen. Let's fix the webcam. Delete you. Yeah, that's what we want. Sweet. There we go. Now I'm not frozen anymore. Okay. Advanced force on a wire. So basically, the only thing that makes this thing advanced is I tell you less information than I told you yesterday, or I tell you more fundamental information, earlier information that you're going to start having to put together. Basically, what this is going to involve is this. You're going to have to find the external B field. Caused by whatever. Either a wire rather, or a coil. And then 2, you have to find the force on some other object. Let's get some other wire, we'll say. Okay, that's basically it. We can talk through example 1 here. Example 1 says, find the field direction for wire 1. The field point is where wire 2 is located. Then find, that should say find, not field. Find the force on wire 2. The wires indicate current direction. So, we want to find the field direction for wire 1. Wire 1 is here. At wire 2, what's the direction of my magnetic field? So which right-handed rule are we using? The first one, yeah, the thumb in the direction of the current, and then your fingers curl around in the direction of the magnetic field. So the force from this, the magnetic field from this wire here is going in what direction where wire 2 is located? It's going into the page, correct. So over here, this thing's going in. So if it's going in over there where wire 2 is, what is the direction now on the force for wire 2? So which right-handed rule do we then have to involve? Yeah, the finger guns, rule 3. Your pointer finger goes in the direction of the current in the wire. Your middle finger goes in the direction of the magnetic field. Your thumb is then the resulting force direction. So that's the direction of my current. That little X means the sucker's going into the page, so my middle finger has to go that way too. Then my thumb, stubby little thumb, is pointing to the left. So we've got a direction for the force on wire 2 that way. Cool? B. What's going on in B? Sorry? Parallel, so they're going in the opposite directions. We want to find, ultimately what we want to do is find the force on wire 2. So to do that, I need the magnetic field from 1. What's the magnetic field direction from wire 1, where wire 2 is? It's going into the page, using right-handed rule 1. So it's going into the page, and my current is going down the page. What's the direction of the force on wire 2? We agree with Joseph? The force on wire 2 is going this way. So an extension of that, what direction would the force on wire 1 be? Yeah. The other way. F on 1. Okay. C. What's the direction on the direction of the magnetic field and the force on wire 2? It's going into the page. So if my magnetic field is going into the page, and so is my current for wire 2, what's the force on wire 2? Why is there none? Because the current and magnetic field are parallel to each other. Cool. There's no force. D. What's going on here? They're going the same way. So the magnetic field created by 1, where 2 is what? The magnetic field. Magnetic field is going into the page again. So what's the direction of the force for wire 2? So it's going to go to the left. So it's going to move inwards here. Force on 2. So then the force on wire 1, what happened to wire 1? Yeah, it's going to pull these things together. It's going to be equal and opposite. Yeah, because it's that whole region. So now let's actually do it using values. There is a device known as a current balance, which is used to measure magnetic fields. A wire strip is placed inside the coil. The coil provides the external magnetic field. When a current runs through the wire strip, it experiences a force. Ends up looking like this, and this is going to be the basis for a bunch of the questions that we do for examples on the next page. What is the direction of the magnetic field in this coil? Which right-handed rule are we going to use to figure that out? It's going to the left, you say. So we're using right-handed rule 2. My fingers are now, because this is a coil, my fingers are going in the direction of the current in the coil. My thumb then goes in the direction of the magnetic field. So it goes that way. There's my B field. So I'm going to add that to the picture on the bottom. So my B field's going that way. I've got a current carrying wire as a loop. This little arrow here is the direction of the current. It goes this way, then it goes down, then it goes this way. What parts of that wire loop experience forces? Just this piece here. Why, Zach? Okay, so this guy, color blue is probably the bad choice for that because blue looks an awful lot like black. But Zach, you're right. The only piece that experiences magnetic force is that little strip right there, because this guy and this guy have current that's going parallel and anti-parallel to the direction of the magnetic field. So the force on this guy is going to be 0. The force on this piece of wire is going to be 0. So what you're going to get here is a force on this piece. Which direction? That's supposed to be I screwed up. Oh. We can agree it's down into the page. I shouldn't say down. I should say into the page. Into the page. So we're cool with how this could then function as a balance. Yeah. Magnetic field gets turned on. This piece, if we're looking at this thing from the top down, it's going to tilt in, causing some meter over here on this side to then tick up. The strength at which this thing tips down can relatively easily be converted into the strength of the magnetic field. That can be pre-programmed into a device that you can just kind of carry around, because it's going to end up looking something like this. Oh. So here's the top view. Here's the side view. So this is the same object from the top and from the side. This is how this thing is set up. We've got our wire strip. We've got this thing here. We've already established on this one the force is on that little strip. It's into the page for that guy there, which means I'm going to have a force this way. in this diagram. F mag. I'm using this thing as a balance, so I've got some counterweight over here. I've got a pivot point right there where these two things can seesaw around. So this looks an awful lot like everyone's favorite awful chapter. This is torque. Okay? You've got a magnetic field causing this thing to rotate about a pivot. When there's no magnetic field, this thing's balanced. The balance is coming from what? The counterweight and the mass of the weight of the wire strip. So if there's no magnetic field, that thing's going to be balanced as soon as we generate a magnetic field. It's going to rotate. In this case, it's going to rotate counterclockwise, yes. So let's go play with it. We've got some information. The same setup. We've got, we're told that the coil, the solenoid, this guy here, has a current running through it of 5 amps. There are 1,250 turns per centimeter. Turns per centimeter is not a super useful measure because everything we deal with is in terms of meters. So let's convert that to turns per meter. 1,250 turns per centimeter. There's 100 centimeters per meter. So how many turns are there per meter? Yeah, we're going to add 2 zeros. So we're going to get N is going to be, well, we had 1,250 turns per centimeter. It's going to be 125,000 turns per meter. Good morning, gentlemen. Lucas, you have to give up a sense. What sense are you giving up? Sense, yes. Smell, okay. Ben's, hey, Ben, same question. Hearing. See, Ashley, you don't want to expose the loopholes to everyone. One of them may have found it on their own. But you know what? No, it worked. I liked your answer to it. Okay, so back to this. We've got 125,000 turns per meter in this solenoid. We've got a current going through the solenoid of 5 amps. We've got a current going through the little strip here of 2.5 amps. And this is a 2 centimeter little strip of wire that's experiencing a magnetic force. 2 centimeters, not a useful value. When we're dealing in physics, everything needs to be in meters, kilograms, etc. So that is going to be what length? 0.02 meters, because there's 100 centimeters in a meter. So now we can go through, we can actually find this thing. We want to find the force on the left end of the strip because we do know that there's a magnetic force downwards. And the mass we want to find is the mass over here required to balance this. So this is going to give us some Fg going on downwards there. Sorry? We haven't done any of it yet. We're going to have to. So let's kind of just do it all at once. To find the force here, F equals the force on a wire in a magnetic field is given to us by what Zach just said, F mag equals LIB, where L is the length of the wire experiencing the force. Length of wire experiencing the force. Wow, that's really tiny and probably hard to read. I, which current is that? Which one though? We have 2. We've got one in the coil, we've got one in the strip. The current of the strip. So it's the current of the wire experiencing force. Just doing some review for the people who weren't here yesterday. And And B is the mag field from the coil. Which, Zach, you've already pointed out we don't know. So let's go rectify that first. We need B from the coil. How do we find the magnetic field produced? We already know which direction it's in. It's that way. What's the formula for the B field of a coil? Mu naught little n times I, where mu naught is a constant found on the formula sheet, n is your turns per meter, and I is the current in the coil. So mu naught is 4 pi times 10 to the negative 7. Little n, the turns per meter, is 125,000. And the current in the coil is what? 5 amps. It's this information right here. That's all the coil stuff. Got to make sure you keep things, the pieces straight. I want the magnetic field from the coil, so I need to know the current in the coil. So the B field of the coil is what? 0.785. Can someone verify that? Okay. Units for mu. Magnetic fields are measured in Teslas.
Right.
After everyone's favorite disenfranchised physicist. If he's not, he should be. Go do some reading. The guy was nuts and awesome. He invented things like 100 years before other people invented them, and then just destroyed them and got rid of the plans. No, his name is Musk. His name is Musk. He is a fantastic entrepreneur, not necessarily an inventor himself. Yeah, no, he's no Nikola. The guy worth remembering. So now we've got the B field of the coil. We can insert the information we've got over here to find the magnetic force. So F mag on the strip, bless you, is going to be given to us by L, the length of the wire experiencing the strip. How much of the wire is experiencing the force? 0.02, that little length right here. The current in that strip is 2.5 amps. And the B field it's experiencing, 0.785, what we just calculated. So F mag, can someone verify that value? Ashton, you're good too. 0.0, say that again, Zach. 0.039, and that's a force measured in newtons. Okay, so making progress. We don't have the mass of the strip. We're going to assume the mass of the strip is very, very small compared to, they don't provide it for us. So the mass of the strip is going to be very small compared to the magnetic forces it's experiencing. So now to find, that's part A, to find the mass required to balance this thing, whenever you hear the word balance, you should think equilibrium. When you think equilibrium, you've got three options. Forces up equals forces down, left equals right, and the sum of my torques are equal to 0, or torques clockwise equals torque counterclockwise. This thing is resting on a pivot. So what are we going to have to deal with? Torque. Okay? We've got a pivot. So what we want to do here for B is we want to balance torques. So our torques clockwise are going to have to equal our torques counterclockwise. How do we calculate a torque? A perpendicular force acting on an object some distance from the pivot. Multiply that perpendicular force with that distance to the pivot. That gives you the torque. So we're going to have F mag perp times R. I'll call it R mag. And our counterclockwise, ooh, that was our counterclockwise torque. Whoops, I'm just going to make that 2 C's, and that's 1 C. Cool. Counterclockwise is on the left now. And this guy here is going to produce a clockwise torque. This guy's going down this way. This guy's going down this way. Torques get drawn. So I've seen some of you practicing these things. Those of you shall remain nameless. But we want to make sure we draw the forces. And then after we've drawn the forces, we identify the torques. Those are separate quantities. So this is our clockwise, that's our counterclockwise. I just tweaked this so counterclockwise equals clockwise. This guy here then is going to be FG times RG. So now we can fill in these values. 0.039. It's 12.5 centimeters away, which needs to be in meters. 0.125 is going to equal, that's going to be M times 9.8, because we're looking for the mass, not the weight. Times the distance of the mass to the pivot. It's 2.5 centimeters, so that's going to be 0.025. Find me M. Because we did a lot of it for I guess. I'm hoping it just fits. Yeah. 0.02 kilograms. Point 0.02 kilograms. So we don't have 0.02 kilograms. Doesn't really make sense with us conceptually. So what is 0.02 kilograms in a mass that you can, relate a little bit closer to? It's 20 grams. 20 grams is, if you've played with gram weights before, I'm hoping in Physics 11, I'm hoping Morrison got you to do a bunch of labs. Who knows? You were supposed to. 20 grams is not a lot. Okay, flip the page. Let's amp it up a little bit here. No pun intended. Okay, so we've got a different little scenario here. We've got a magnet, a north pole of a magnet, a south pole of a magnet. We've got a loop here attached to a circuit. This is the front view. This is what it would look like, like looking at its face. Looking down at it from the top, you'd see something that looks like this, north pole, south pole, and a current loop that remains like this. What happens to a loop of current that is placed in a magnetic field? The loop of current is seen below the power supply in both front and top view. As soon as I turn the current on here, what's going to happen? Is the question. Who wants to reason their way through this one? Okay, give me any piece of it. That's our setup. What do you know? What flows from north to south? Okay, so our B field's going this way. Okay, what else do you know?
The bits that are parallel with the B field.
So which are those bits? The tops, okay? So there's no force here. And there's no force down here on either one of these little pieces. Which one's up, which one's in? Hey, Miss Pearson, what's going on? Yeah, Crystal, where are my meter sticks? Awesome. Okay, so let's take it back a step. Before we can identify which way the forces are, what do we need to know? The direction of the current in the wire? Current was a long time ago for some of you, so let's review it. Current is going which way here? It goes, counterclockwise through this loop. It goes from the positive to the negative. That's not the direction the electrons are going, but that is the direction that we call conventional current. So current's going this way. And then that way, and then that way, and then this way. Then that way, 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 that way.
And on the top, B field is going up.
So that is the direction of our current. I'm going to call that I. So now, if we know that's the direction of the current, the weed off. Get your act together. That's going that way. That's going that way. That's going that way. There we go. That makes sense. Zach, you were commenting on the direction of the force on those different parts of the loop. It's going to twist. So which side's going up, which side's going in? Want to run that one more time? Right-hand rule that again. Okay, so we're going to right-hand rule this. Pointer finger in the direction of the current. Magnetic field is my middle finger. My thumb is the direction of the force. So on the right-hand side, you're using your left hand, Zach. It's a right-hand rule. Right-hand rule, big guy. It's early on a Friday. It's been a long week. Right-hand rule means you have to use your right hand. The universe is prejudiced against lefties. So on this side, my force is going in. On this side, my force is going which way? Can't both be going in. Because the current's going down, my magnetic field's going that way. So that's going upwards. So my force this way is up over here. It's down over there. If I look at it from the top view, this guy's going this way. This guy's going that way. So what that means is this current carrying loop is going to go and twist or torque. This is the top view. So I take this and I just tilt it up, and this is what we would see. So this Fx into the page, if I tilt it up, is going now up the page. This guy that was going into the page tilts towards us, going down the page. So we're going to get an object. The loop is going to go like that. These are just the forces. Those forces are going to create a torque. That torque is going to cause the loop to spin. An application of this, we've all used an ammeter, right?
I know what it is.
Hands up if we used an ammeter, an analog ammeter. Oh, Mr. Morrison was supposed to do labs. Okay, ammeter looks like this. Little box. You plug your current into these things, and it tells you what the current is. Here's how that works. The current you plug in, you plug the ammeter in series, so that it becomes part of, this could be a larger circuit. Your ammeter gets plugged into a chunk of it. The current flowing through the ammeter goes through a coil. That coil is, or that box has magnets in it. So there's a magnetic field going on here. While the ammeter is not plugged in, there's no current going through the ammeter. It does nothing. As soon as you plug it in, assuming the current's going this way, it's going to torque, giving you some reading of the current traveling through that loop. Ingenious little device. Which is why, I don't know if you guys ever played with it, if you flip the leads around on the thing, the needle's going to go the other way. Because now the forces aren't this way and this way, they're this way, causing the ammeter to go like that. Real simple device, an application of magnetic force on a wire. The last application of magnetic force on a wire we're going to look at is something called magnetohydrodynamics, which is pretty cool. Hands up if you've seen the movie The Hunt for Red October. Only one of you have seen Hunt for Red October? Okay, you gotta watch it. I'm not gonna watch it with you here, but The Hunt for Red October, there's so many reasons why it's so classic. It's based on a Tom Clancy novel of the same name. It takes place during the Cold War, like everything else Tom Clancy does, which you probably don't know him because he's dead. Rainbow Six, yes. Okay, the guy who wrote Rainbow Six, video game based on a book. The book's amazing. So The Hunt for Red October is based on this idea that there is the Soviets, because they're the Soviets at the time, they're not Russians, they're Soviets, have developed a nuclear submarine engine that has no moving parts. And the premise behind it is this. This is exactly the premise behind the propulsion of that submarine. The idea here is that salt water is a good conductor of electricity. So by charging the water and running a magnetic field above and below it, you can accelerate the water through your submarine. Every force has an equal and opposite, or for every force there's an equal and opposite force. That would then, the water shooting out the back propels the submarine forward. In practice, the amount of power required to do this is substantial, which is why it has never actually been feasible. And the speed, like the acceleration on these things isn't great for us. Like pushing something through the water isn't super effective like this. But the premise of the book is that the Soviets have done this. That submarine captain with this is like, this is a silent nuclear boat. We can put nuclear missiles wherever we want. This is dangerous. The Russians shouldn't have this. I'm going to defect. He tries to defect to the United States because the United States is always the good guys in Tom Clancy novels. In the movie, it's played by everyone's favorite Scottish-Russian actor, Sean Connery. But yeah, Hunt for October is delightful, and that you don't know what it is takes a little bit away from this question, but that's okay. Magnetohydrodynamics is the concept that we're looking at here. So the idea is to run a current through seawater while the seawater is passing between large magnets. These X's here represent the direction of the current. So the current is going through the boat right to left, because this is the front of the boat, this is the back of the boat. As the water goes through, we run the current through this section by running a magnetic field this way. Using your right-hand rule, what's the direction on the force on the water? It's going to be back. So the water experiences a force this way. For every action, there must be an equal and opposite reaction. So the force on the sub has to be forwards, propelling you forward. Again, in practice, the power required to do this is astronomical. But, I mean, nuclear reactors produce an astronomical amount of power. So that's kind of the only one where this is theoretically possible. But it's a neat concept. Given more information, we could find the acceleration of the boat, given the strength of the magnetic field, the current that it's producing through the seawater. That'll give you the force. The force on the boat is equal to and opposite. The mass of the boat is obviously much larger. You can find the acceleration on the boat, and then it becomes a kinematics problem. Yes, where's the hell?
No, that's the kind of one.
Yeah, they tell us those X's are.
Oh, that's
It's going from right to left. Which is the only way it can be if you want the force on the water to be back. You flip the direction, which would be an interesting little braking system. You flip the current here, all of a sudden now you're propelling the water forward, bringing your forward motion to a stop. This submarine could theoretically go backwards.
the sub's like full of water. It's a big one.
What do you mean full of water?
Yeah, it's a big one.
Well, it's fundamentally no different than a jet turbine full of air the whole time. Sucks it in the front, accelerates it out the back, pushing the plane forward. It's theoretically the same thing. There'd be big intakes on the side of these things, scoops of some kind. How they'd engineer it, I don't know, because that would create a bunch of drag. But yeah, you'd have scoops or intakes somewhere on this thing that would theoretically open and close. I don't know how it's connected.
I don't know, it's just the way I'm imagining. Like just a giant, like I feel like they would.
So, and the beauty of this thing is that it would run silently, compared to the diesel engine that these things the submarine operates on normally. Sorry?
So they wouldn't have to worry about radar.
Sonar, but yeah. Not even sonar. There are acoustic microphones all over the seafloor. The United States and the Russians and the Brits have littered the seafloor with acoustic microphones, so they can hear who's traveling where. These are all wired up. At any point, they can hear what's going on different places in the ocean. Sometimes it's whales, sometimes it's enemy submarines. This thing could theoretically travel silently, bypassing all of that. Which though not on radar because it's underwater. Sonar, but active sonar isn't always used. Active sonar screws with sea life. Active sonar also gives up your location, so they're hesitant to use sonar. But a boat that runs like this silently, if you don't know it's there, you don't turn on your active sonar. The whole premise of the movie was they could park a boat like this with a whole bunch of nuclear missile tubes in the harbor next to the Statue of Liberty and just bomb with impunity. That's the premise of the movie. Great movie. Highly recommend it. If I'm not mistaken, it's actually on Netflix. So it's Cold War was the premise. So practice some of this stuff. The questions I'm going to assign to you are this. Make sure I get the right ones. Oh, wow, you're close, Joseph, actually. I want to make sure it's consistent with the ones I've put online. I want you guys to do the following. I want you to do 1 to 3. I want you to do... Ooh. You know what? I'm sorry, guys. I want you to do 1 to 6. I'm sorry, but I'm not sorry. I want you to do... Oh, you know what? No. There's just so many interesting applications on this. I want you to 1 to 9.
Oh, no.
1 to 9. The reason for like 7 is your rail gun that Zach was interested in yesterday. 8 is actually find the force on the boat. We could extend question 8 further if we wanted to, but 1 to 9. That's what I want you to do. You got lots of time before we do the next lesson, which is the last lesson in this section. May the force be with you. Physics is just so easy to have puns. Yes, Crystal.